my name is Laura Belko, and I'm going to present our work on precomputed radiance transfer using a data-driven paradigm. This is a joint work with Thomas Dolio, also from Unity, Willem Barbier, while he was studying at NCMAG, and Cyril Soler from INRIA. Our target is to render indirect illumination on a single asset in real time, such as this mage lizard. Here, adding global illumination to the skin and hair really enrich this asset's appearance compared to direct illumination only, as you can see on the right. To compute global illumination in real time, a large panel of techniques are available. On one end of the spectrum, it is possible to bake global illumination and fetch its values at runtime. This is typically what is done using light maps. However, this restricts the lighting to be static. On the other hand of the spectrum, it is possible to compute global illumination completely at runtime, for example, using hardware-accelerated ray tracing. While this allows to have dynamic lighting, it incurs every computation at runtime. In the middle exists precomputed radiance transfer, a baking technique that allows for dynamic illumination at runtime. Precomputed radiance transfer was pioneered by Sloan and colleagues, follows the following principle. In a baking stage, a transfer matrix is precomputed, usually one per vertex of the asset. At runtime, this matrix is used to convert the projection of incident illumination in a directional basis to coefficients representing the outgoing radiance in possibly the same directional basis. This efficiently solves dynamic global illumination on single assets, however, with a few caveats. First, its frequency content is bound by both the projection basis for the incident radiance, but also by the asset's tessellation. This can cause light leaking and interpolation artifacts. A second caveat is that this baking process requires a dedicated solution since the projection basis acts as an implicit light source that we have to account for, and this prevents to fully reuse existing baking solutions. With the rise of machine learning, it would be tempting to replace precomputed radiance transfer with neural networks. And in fact, some have looked at this idea of reproducing precomputed radiance transfer architectures with neural networks, such as the work of Reiner et al. To build such a solution, one needs to have access to a specific database of indirect illumination for different light configurations. And we were surprised to see this idea of using neural networks go forward right away, given that we have access to this same specific database. Indeed, once you have access to this database, an intermediate step is possible. And this intermediate step leverages the data available to neural networks, so we are going to look at this problem of dynamic global illumination, again, for key assets and low frequency appearance, but we are going to construct precomputed radiance transfer in a data-driven fashion. We are going to make the hypothesis that we are only interested in reconstructing light conditions observable at runtime, and that our database reflects this space. We are going to showcase such approach in different light transport scenarios, such as light transport on surfaces, in volumes, or in air. To understand how we build our data-driven formalism, I'm going to look at the case study of a particular scene, and note that this will mostly be an intuitive explanation. If you're interested in the mathematical details, please refer to the paper. Okay, let's start by assuming that we have access to a database of renderings for direct illumination for this Viking room scene. And let's assume that our database is enough to permit us to reconstruct any light configuration we are looking for. That is, for a given light configuration, we can evaluate its associated direct illumination as a weighted sum of the database elements. Here, the direct illumination X is reconstructed as a weighted sum of the database list elements with coefficient CK. Since light transport is linear, if we have the dual database consisting of renderings of indirect illumination, we can reconstruct the indirect illumination associated with the given light condition by doing a weighted sum of the indirect illumination database, but with the same coefficients we used for direct illumination. In other words, if we know how to project the light configuration into the direct illumination database, we can evaluate its indirect illumination. And while this is theoretically sound, there is a catch, or at least two. First, we don't have access to the database of indirect illumination at runtime, and this would weigh too much memory and requires too many texture fetches to be viable. Second, we don't know how to evaluate the weight coefficient for a given direct illumination configuration. So from this, we show how to build a simple model for data-driven precomputed radiance transfer. And we do so by building a meshless reconstruction basis to access the indirect illumination database, and we provide an efficient measurement of the coefficient through a sparse evaluation of direct illumination and also using a transfer matrix. It is not possible to store and use the full database of global illumination at runtime. However, we found that for the different test scenes we used, the effective dimensionality of each dataset was quite low. In this plot, you can see the error when reconstructing the complete database with an increasing number of its eigenvectors. For most of the scenes we used, 9 to 10 eigenvectors are sufficient to capture most of the energy. That means we can well approximate indirect illumination using only a handful of basis elements. Those are easily extracted using singular value decomposition. One last step is that we cannot store rendering using a fixed viewpoint for our database. While it is possible to store radiance information at the vertices of a mesh, much like PRT does, we found it better to use texture mapping. This even permits to reuse already available baking solutions, such as lightmap bakers. We end up building our database with many lightmaps that are later decomposed in the table basis using the SVD. To compact storage, we choose to share the basis for all the color channels and to pack them into RGBA texture. It follows that reconstructing the indirect illumination with 16 bases will require 4 textures at runtime. Okay, now that we have a way to build and access a database of indirect illumination, we need to do the same for the direct illumination. Instead of projecting the incident lighting into a basis, we choose to measure direct illumination at a sparse set of locations on the axis or on its convex hull. For that, we use a small deferred shading path on a fixed G-buffer with precomputed position and normals. These positions are evenly distributed using sample illumination, and you can see them on the screen. This permits to build a database of direct illumination measures and evaluate it during runtime. However, we are still left with the task of computing the coefficient for a given vector x with respect to the database. But we won't need an explicit way of computing them. We show in the paper that we only need a transfer matrix for that. Why so? Because the database produces a mapping between the direct illumination and the indirect illumination. It does so by storing for each random light configuration both a direct and an indirect vector. Indeed, we use the measurement points to evaluate a vector of direct lighting. and the decomposition of the associated light map of the indirect illumination in the basis produces a vector of coefficient, here u0, to reconstruct the indirect illumination. So we indeed have a mapping between the vector of direct illumination x0 and the coefficients of indirect illumination u0. And when we build the database, we accumulate pairs of vectors. And this results in two matrices. First, X that describes the direct lighting, and U that describes indirect lighting. For those matrices, we can extract a transfer function that maps direct illumination to indirect illumination. In our case, we choose to use least square regression to build a transfer matrix M that converts any direct illumination vector into coefficient of indirect illumination. Implicitly, M encodes the projection that gives the coefficient to decompose direct illumination in the database. Okay, now we need to put everything together for our runtime algorithm. Given a light configuration, we rasterize and shade direct illumination on our asset. Then, we load the small G-buffer of measurement points and perform a deferred shading pass on it. It outputs a vector of direct illumination, x. We multiply this vector by the precomputed matrix, transfer matrix M, using a compute shader. This provides a vector of coefficient that we multiply by the basis stored in the textures. This gives us the indirect illumination in UV space. We do the last step in a fragment shader or in the deferred pass, and this avoids to compute texels that are not visible by the camera. And that's it. We have our indirect illumination on our asset that we accumulate with the direct illumination to get our final result. A nice property of our method is that it is very simple to extend for animation. Actually, in some cases, this is as simple as building a dataset with random poses, as you can see here, where we got direct illumination on the left and the indirect illumination on the right for different light configuration and animation poses. We experimented that we could share most runtime's elements, such as building a single matrix basis for the whole animation, or even using a single transfer matrix. We implemented our method in Unity using the high-definition random pipeline. There, we used the rendering tools already available to construct the database. The light mapper for surface transport, and RTX implementation of volumetric and fiber-to-fiber transport for this later case. Our method only requires a small update at runtime on the standard shader. We show that our method permits to reconstruct indirect illumination with a varying quality depending on the number of bases. As you can see here, the reference is on the left, and as we increase the number of bases, we get closer and closer to the target result. We validated that the transfer matrix does not impede the quality of reconstruction. In this graph, we compared the error of reconstruction using either our method or directly using the basis and project the indirect illumination inside it. Our method overhead compared to no GI at all is reasonable, but also that we are far from the cost of real-time path tracing, even for low sampling budget. Here is a recorded result of an animated asset. On this asset, we have simulated volumetric light transport inside it. We do not rely on any BSS-RDF approximation here and use full path tracing to evaluate the indirect illumination. Because there is no surface material here, we use a white immersion material to capture direct illumination. In this example, we share both the basis and the transfer matrix for the whole animation. So the only source of variation across frames is because measurement points are attached to the geometry. Here is the asset in this animation. And here is the rendering of the measurement points. As you can see, they are attached to geometry. And this is why the measurements vector is evolving, even though the light condition is not. This makes the reconstructed light map reflects the changes of incident illumination on the asset, on the different part of the asset. And using 64 basis vectors, we can reconstruct the following appearance, which follows the reference here on the right. Here is another result, this time for fiber-to-fiber scattering. For this asset, we had to generate a dedicated UV space to pack radiance on the fiber as 2D textures. Here is a rendering of the indirect component only, aside the reference, and combined with direct illumination. And the same rendering of indirect component only again, and with direct illumination. While we can handle a variety of things, our method knows some limitations. For example, we assume that the database corresponds to the light conditions encountered at runtime. If our method is used with light conditions outside of the dataset, the resulting indirect lighting will depart from the reference. We did not attempt to reconstruct rough appearances. While our formulation is not restricted to diffuse appearance, it would require more work to encode directionality in the database, for example using spherical harmonics. Also, our method is not well suited for baking indirect illumination in large assets. There, a modular approach, like the one of Luce and colleagues, would be required. That's it for our talk. As a summary, I presented a reformulation of precomputed radiance transfer using a data-driven formalism. This allowed us to build a simple and efficient algorithm for real-time rendering of indirect illumination. We believe that it should be used as a baseline for neural network methods, since it permits to benchmark what improvements nonlinear function can bring. Thank you for watching.